A function f is even if f of x equals f of minus x and is odd if f of minus x equals minus f of x. Part A. By constructing suitable linear combinations of f of x and f of minus x, or otherwise, show that any function can be written as the sum of an even function and an odd function. So we have to write a general function in the form f sub e of x plus f sub o of x, where f sub e of x is even and f sub o of x is odd. And we note that this symbol means that both sides are equal for all values of x. In other words, both sides are identically equal. And we recall that by definition, this identity holds for f sub e, and this one holds for f sub o. Now we have to construct suitable linear combinations of f of x and f of minus x, where a linear combination is an expression of this form. And so to start, we write f sub e as a linear combination of f of x and f of minus x, and also f sub o. Now we have to work out the values of a, b, c, and d, and to do so, it is clear that we will have to apply the defining properties of f sub e and f sub o, which we do as follows. We set x equal to minus x, so that f sub e of minus x equals a times f of minus x plus b of f of x, and that f sub o of minus x equals c times f of minus x plus d times f of x. And then the defining property of f sub e tells us that this quantity equals this quantity, giving this equation. And the defining property of f sub o tells us that the negative of this quantity equals this quantity, giving this equation. And now we can rearrange this identity as follows. Now we want a result that is true for an arbitrary function, but we know that this quantity cannot be identically zero for odd functions. And so we must have a minus b equals 0 so that a equals b. We follow a similar procedure for this identity. We note that this quantity cannot be identically 0 for even functions, so that c equals minus d. And now we put together this fact and this fact to find that f sub e of x equals a into f of x plus f of minus x. And we put together this fact and this fact to find that f sub o of x equals c into f of x minus f of minus x. And recalling that f of x is identically equal to f sub e of x plus f sub o of x, we find that f of x is identically equal to a plus c times f of x plus a minus c times f of minus x. We have to find the values of a and c, and to do so, we rewrite f of x in the form 1 times f of x plus 0 times f of minus x, which allows us to equate coefficients as follows. And on solving the simultaneous equations, we find that a equals 1/2, c equals 1/2, from which we find that f sub e of x equals f of x plus f of minus x over 2, and that f sub o of x equals f of x minus f of minus x over 2. And finally, we have that f of x is the sum of those two functions. Now, we haven't actually checked that f sub e of x is even, but we can easily do so as follows. And similarly, we can check that f sub o of x is odd. Although we have found an expression for f of x as required, that was rather long-winded, and in fact there's an alternative method that is very much quicker. And so otherwise, we write f of x as f sub e of x plus f sub o of x, so that f of minus x equals f sub e of minus x plus f sub o of minus x, which becomes f sub e of x minus f sub o of x, on applying the defining properties of f sub e and f sub o. And those two results give us simultaneous equations for f sub e and f sub o, which we solve to find that f sub e of x equals f of x plus f of minus x over 2 as before, and that f sub o of x equals f of x minus f of minus x over 2 again as before. Part B. Show that for even f of x, the integral from minus a to a of f of x dx equals 2 times the integral from 0 to a of f of x dx. And that for odd f of x, the integral from minus a to a of f of x dx equals 0. These are two standard results with which you should be familiar. Here is the defining property of an even function, and here is a representation of an even function from x equals minus a to x equals a. We see that the green area represents the integral from minus a to 0 of f of x dx, and that the blue area represents the integral from 0 to a of f of x dx. And we can see graphically that the green area is equal to the blue area. We can write the integral from minus a to a of f of x dx as the sum of those two integrals. And now we show that the green area is equal to the blue area by reflecting the green onto the blue via the transformation x goes to minus x, which maps points as follows. And to apply that transformation algebraically to the green integral, we make this substitution, from which we easily obtain the following results. And applying those to the green integral, we obtain the integral from a to 0 of f of minus u minus du, which becomes the integral from a to 0 of f of minus x minus dx, on noting that u is a dummy variable. And we use the minus sign in the minus dx to swap the integral limits to obtain the integral from 0 to a of f of minus x dx. And now we apply the defining property of an even function to obtain the integral from 0 to a of f of x dx for the green integral. And the green and the blue integrals are now identical, so we add them to obtain 2 times the integral from 0 to a of f of x dx. Here is the defining property of an odd function, and here is the graph of an odd function from x equals minus a to x equals a. The red area, which is negative, is the integral from minus a to 0 of f of x dx. And the blue area, which is positive, is the integral from 0 to a of f of x dx. And the integral from minus a to a of f of x dx is the sum of those two integrals as before. And to derive the result, we reflect the red area so it is below the blue area. And we do that via the transformation x goes to minus x, as before. When we make that transformation, we obtain a graph as follows, where the red area now lies below the blue area, and with the lower integral being the negative of the upper integral. We're using the same transformation as we did in the even case, and so to show the result algebraically, we use the same set of substitution results as previously. And so the working proceeds almost identically to the point where we apply the defining property of an odd function. And we now pull the negative sign out of the first integral, and we see that the integral on the left is the negative of that on the right, and so they add to 0. it can be shown that the integral from 0 to infinity of e to the minus x squared dx equals root pi over 2. Part C. Evaluate the integral from minus infinity to infinity of e to the minus x squared over 1 plus e to the x cubed dx, and hence evaluate the integral from minus infinity to infinity of e to the minus x squared over e to the 2 pi x into 1 plus e to the sine x dx. Now, presumably the previous results were not just for fun, and we're going to have to use them, so we note them down here for reference. And given the symmetrical limits on the integrals that we have to evaluate, we can combine these results usefully as follows. We take an integral with symmetrical limits and we rewrite the integrand as the sum of an even and odd function, which we know can always be done. We split the integral of a sum into the sum of integrals, and we apply the results from part B to obtain the integral from minus a to a of f of x dx equals 2 times the integral from 0 to a of the even part of f of x dx. And since f sub e of x is given by this expression, we can rewrite that as 2 times the integral from 0 to a of f of x plus f of minus x over 2 dx. And that result is true for an arbitrary function f of x. Now, for the integral in question, we note that the limits are infinite rather than being finite. But for the rest of this question, we're going to assume that that doesn't cause any problem. And so we equate the integrand that is given with f of x, and to use the results above, we must of course evaluate f sub e of x as follows. At this point, we notice that we have factored out e to the minus x squared, but we should also note that we can only do that because e to the minus x squared is an even function. And so e to the minus x squared was left unchanged under the substitution x goes to minus x. We now simplify the fractions with more algebra as follows. And at this point, we notice that e to the minus x cubed times e to the x cubed equals 1, a nice result, because it allows us to make the following simplification, where f sub e of x is the numerator of f of x divided by 2. And we can note that the numerator only cancelled with the denominator when we were combining the two fractions, because e to the minus x cubed times e to the x cubed equals 1. And so we have that the integral from minus infinity to infinity of e to the minus x squared over 1 plus e to the x cubed dx becomes the integral from minus infinity to infinity of e to the minus x squared over 2 dx, which turns into 2 times the integral from 0 to infinity of e to the minus x squared over 2 dx on applying this result, which turns into the integral from 0 to infinity of e to the minus x squared dx. So we finally have that our integral, which I have called I, equals root pi over 2. And having evaluated the first integral, we must hence evaluate the integral from minus infinity to infinity of e to the minus x squared over e to the 2 pi x into 1 plus e to the sine x dx. Now, what we have mainly learned is that there was a nice cancellation trick that occurred in integral I. We noticed that the numerators of the two integrands are identical, but the denominator in integral j has a different form. The obvious question here is, can we use the same cancellation trick anyway? And so given f of x as the integrand, we find that f of minus x equals e to the minus x squared over e to the minus 2 pi x into 1 plus e to the minus sine x, bearing in mind that sine x is an odd function. And we combine those results to find that f of x plus f of minus x over 2, after some tedious algebra that we will omit, is this expression, where to obtain the 2 in the denominator, we have applied the nice result that e to the sine x times e to the minus sine x equals 1, but where unfortunately we get no cancellation of the numerator and the denominator due to the presence of these terms. And so the trick that we used for integral I won't work immediately, at least, for integral j. And we will have to turn our attention to the integrand again and try to think how we could split it up in such a way that we could evaluate it. An obvious approach is to split the integrand up as a product, as shown here, where we note that this term can be integrated via the trick that we used in integral I, and that this term is easy to differentiate. And on putting those two facts together, we wonder if integration by parts is appropriate here. But recall that integral I is supposed to tell us how to do integral j because it is a hence question, and bearing in mind that we didn't use integration by parts for integral I, then we conclude probably not. Another way to rewrite the integrand is to bring the e to the 2 pi x term into the numerator like this to obtain e to the minus x squared plus 2 pi x in the numerator. And here we note that the numerator is not an even function, and we don't even know the value of its integral, but the denominator does indeed have the required form. So it's perhaps worthwhile seeing what we can do with this form of the integrand. We can ask ourselves, are there any obvious next steps? Well, given that there is an x squared plus 2 pi x expression in the numerator, then we could perhaps complete the square. And on doing so, we obtain this expression, which turns into e to the pi squared times e to the minus x plus pi all squared over 1 plus e to the sine x. And this looks rather nicer because e to the minus x plus pi squared is simply a translation of e to the minus x squared, and a translation won't affect the value of the infinite e to the minus x squared integral. But we note that we still can't use the trick because the numerator does not contain an even function. If we now rewrite j using the new form of the integrand, we obtain e to the pi squared times the integral from minus infinity to infinity of x to the minus x plus pi all squared over 1 plus e to the sine x dx. And we once again ask the question, any obvious next steps? Well, yes, there is indeed an obvious next step, and that is to change the variables by a u substitution. And on making the obvious substitution, we find that j takes this form, and now the next obvious step is to use a sign identity, sine of u minus pi equals minus sine u, to rewrite j like so. And now we have an even function in the numerator, and we note that since e to the minus sine u times e to the sine u equals 1, the nice property in the denominator that we need, we are done. And on reusing the result that we found for integral I, we find that j has the value e to the pi squared times root pi over 2.